So we are going to be finishing chapter 5 today. Today is Monday. That means that your problem set for chapter 5 is due on Wednesday. It's a short one. Okay? And what we're going to start off with today, most of what we're going to do today is related to what we did last class, but quite different, okay? Last class, our big focus was on calorimetry, and we're going to look at some other aspects of heat today. And our very first topic today is something called Hess's Law. And I'm going to explain what Hess's Law is, and then we're going to do some Hess's Law problems. And for those of you that are the type of person that likes puzzles and logic games and things like that, you're going to love this, okay? Hess's Law problems, I actually think they're sort of fun, but of course my idea of fun is a little skewed. But you never know. You might really like them. Here is what Hess's Law says. Okay, and so this is the definition of Hess's Law. But even before I, talk about this, I want you guys to understand something about chemical reactions in general. Okay, some reactions occur in one very quick step. Reactants to products, boom, done. Other reactions occur in a series of steps. Okay, so for example, your original reactants, let's say, I'm going to call your reactants A. Your reactants A are converted to products B. And then products B are converted to something else that's C. And then C is converted to D. And then D is converted to E. And maybe whatever that thing is that's letter E, those are your final products. The point I'm trying to make here is some reactions occur in one quick step and others occur in multiple steps. Okay? But Hess's Law says that it doesn't matter whether a reaction occurs in one step or 25 steps. It doesn't matter. The overall change in enthalpy. Remember, guys, enthalpy is just a fancy word that means what? Heat energy. The overall change in heat energy from your original reactants to your final products will be the same no matter if your reaction occurs in one shot or it takes multiple steps. Okay? And I'll get to this in just a second. All right? Now this is an energy graph. If you're not entirely sure what's going on here, let me draw something on here that might make it look a little bit more familiar. These are my reactants, my original reactants. Here is my final product. And instead of having these lines and arrows like this, what if I draw it like this? Haven't we seen energy curves of this kind of a shape before? Do you remember, let's review for a second. If I have an energy curve shaped like this, that's in general uphill, do you remember, is this endo or exothermic? It's endo, very good. Okay. Here are my original reactants. Here are my final products. This number, 68 kilojoules, okay, that comes from doing a subtraction. The heat of my products minus the heat of my reactants, which is why it's a positive number, okay? the heat of my products, whatever that number is, minus the heat of my reactants gives me a positive number. It's endothermic. Now, this particular graph tells me that to get from here to here, this reaction occurred in 2 steps. Here's one, 2. Okay. This reaction could have occurred in just 1 step, or I could be really crazy and this could take place in a whole bunch of steps. Okay? And this is going to look a little weird, but I'm hoping you'll get the gist of what I'm trying to say here. So I start off here with my original reactants, and instead of just going through 2 steps, I come over here, la 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 la, do 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 do. I do all kinds of crazy intermediate steps, but the point is, follow me, follow me. I end up in the same place at the end. Okay, even though I went this crazy roundabout way to get from my original reactants to my final products, will this subtraction give me a different number? No. Okay, and that's what Hess's law says. It doesn't matter how you get from beginning to end, the overall change is the same. Okay? And I need to make sure, just remind you of a skill here that we've actually done before, but I want to refresh your memory on it. Okay? First of all, what is on this slide corresponds to the graph, that energy curve on the previous slide. These equations in white, these are called elementary steps. All right? Remember on the graph on the previous slide, that whole reaction took place in 2 steps. Okay? We went from our original reactants up to the top of the hill. That would be this elementary step. And then from the top of the hill down to my final products, that's this one. Okay? And they have their own individual heat values. Okay, let me actually just show you something. Okay, this is the first step. From here to there. Watch my finger, or my hand, am I not moving uphill? Would you agree? Okay, when you're moving uphill in an energy graph, it's a positive heat. That's endo. If you're moving downhill, your change in heat will be negative. That's exo. Right? So that's where this corresponds. Now, what is this? Well, this, ladies and gentlemen, is what's called an overall reaction. Elementary steps, overall reaction. And guys, what I am going to do with these elementary steps is I'm going to be adding them together. This is a skill we have done before. When you add equations together, we did this when we were balancing redox reactions. Do you remember that you can cancel out things that are identical on either side of the arrow? Just look at the equations in white. Do you see anything that I can cancel out? Okay, 2NO gas, absolutely. Gone, gone. Can I cancel anything else out? Okay. Why can't I cancel out the O2? I mean, those are the same. Yeah, they're on the same side of the arrow. They're not on opposite sides. When I bring everything down, this is my overall reaction. And this is my overall change in heat. Where did I get this number? I just simply added those 2 numbers together. That's all. Okay? You're going to have to do this when we do a Hess's Law problem. And this is what you will be presented with. Okay? And I think these problems are really, really fun. You may disagree. You will be given in the problem maybe 2 elementary steps, maybe 3, maybe 4. I think there's one in your problem set where they give you even 5. Each one will have a heat value associated with it. Your job will be to manipulate the elementary steps, change them around somehow, that when you add them together, you end up with the overall reaction you are supposed to. Okay? So the problem is going to say, here's a bunch of elementary steps. Manipulate these so that when you add them together, you get this. Now, when I say manipulate, what do I mean by that? Well, there's basically 2 things you might have to do to an elementary step. Okay? Don't even read this. Just move your eyes from this line in white to this one in yellow. What happened from here to here? What happened to the reaction? Yeah, it got reversed. And look what happens to the enthalpy change. And guys, that should make sense to you. If it was endothermic in one direction, if you reverse it, now it's exothermic. Okay? When I say that you are going to have to manipulate these equations, you might have to flip some of your elementary steps. That's something you may have to do. What's something else you might have to do? Move your eyes, please, from this line right here down to here. What happened? Yeah, all the coefficients were multiplied by 3. Well, look what happens to the enthalpy change. It's also multiplied by 3. Do you guys remember, we talked about this last class, what it means for heat to be an extensive property? What does that mean? Yeah, what does it mean?
It's not affected by how, or it is affected. Misspoke. It is affected by how much of the reactants product you have.
Absolutely. An extensive property is affected by how much reacting material you have. We have tripled the amount of reacting material, so we will have triple the release of heat. Okay? So in a Hess's Law problem, you're going to have to manipulate these elementary steps. You might have to reverse some of them. You might have to change the coefficients of some of them. Let's do an example together. Okay? This is what a Hess's Law problem looks like. I am given 3 elementary steps. As I said, each one will have an enthalpy value associated with it. And our job, it says, calculate, and what this really means is calculate the overall change in enthalpy for this overall reaction. This is the one I'm supposed to end up with at the bottom. And guys, I'm starting you off with a pretty simple one, but these can get more complex. I'm going to walk you through my thought process on this, and some of you are going to be able to solve these right away. Let me caution you against moving too fast, because as I said, this is a simple one, they get more complex. Using this method that I'm going to show you will help keep you organized. Here we go. When you come across a Hess's Law problem, start here. Start with the reaction that you're supposed to end up with, and let's take it piece by piece. O gas, not O2, just O. Do you all see somewhere up here? O gas, just O gas. Do you see it somewhere? Where? Which equation? The second one. Okay, here it is. Well, there's a few issues here. Notice, first of all, this is supposed to be a reactant. And right now it's not. But I need it to be a reactant. Any suggestions on how I fix that problem? Flip it around. Okay. So I'm going to have to write this kind of small. If I flip this around, and I'm going to scribble through this one since I don't need it anymore. What happens to this heat value if I do that? It becomes negative, it changes sign. All right, very good. Okay, well, that's great. I have it on the correct side now, but do you all agree it doesn't have the correct coefficient? And it needs to. Right here it has a coefficient of 2, it needs to have a coefficient of 1. What should I do? Okay, you could say it one of two ways. Multiply the coefficients by 1/2 or divide by 2, same thing. And if I do that, what do I do to this number? Do the same thing, divide by 2. Okay, so I'm going to get to a new screen and I'm going to write this a little bit neater. Let me erase that. Okay. I know that looks a little strange. We typically don't have fractions for for coefficients, but we are this time. So that number was negative, and I'm going to divide it by 2. Okay. Let's come back. So I have taken care of this piece. I had it lined up on the correct side. I had it with the correct coefficient. Good to go. Let's move to the next piece. Look up into these elementary steps. Do you see somewhere H gas? Do you see it? Where? Okay. Is it on the correct side?
No.
Nope. Does it have the correct coefficient? Nope. So what are you going to have to do? Reverse it and divide by 2. Same thing we had to do to this one. So let's write that equation out once we fix it. Okay. So we've taken care of this piece, final piece. Do you see it somewhere up in our elementary steps? Is it on the correct side? Yes. So I don't have to flip this one, but what's the problem? Yeah, it's got the wrong coefficient, so I don't have to flip this one, but I do have to divide by 2. So let's write that out fixed. Guys, at this point, I've taken care of all pieces. I'm ready to add these together. Do you see things I can cancel out? What can I get rid of? Okay, 1/2 O2, what else? Okay, anything else? Let's bring everything down that I have left. Is that the reaction we were supposed to end up with? Yes. Okay? Now, I did not have to come up with this. I mean, this was given to me. The only reason I'm going through all of these steps is, number one, to make sure I end up with what I'm supposed to. But the point is, I need to find a number right there. If you add up those enthalpy values, this is what you will get. That is actually what they asked us to find. Okay. Now, as I said, this was a pretty simple one. And those of you that are very good at things like this may not have needed to write all of this out. But these are going to become more complex, okay? And let's say you don't write all of this out and your number is just a little bit off and you haven't shown me any work. I can't give you any partial credit for that. So it is in your best interest to go through this process. I'm going to have you do one on your own, but before I do that, let me just answer one other question that came up on Friday. The question was, do the states of matter matter? Yes, they do. Okay. For example, if I had, actually, let me come back to the problem written out. Let's say this 1/2 O2 was gas, gaseous in its form, and this 1/2 O2 was liquid. I could not cancel them out. In order to cancel things out, they have to be identical. Okay? So, you try this one on your own. It's a little bit more challenging, not a whole lot. Try it. So, here was the part that was a little tricky with this. Writing these three out wasn't such a big deal, but then when you start looking at what's going to cancel and what's not, okay, the carbon's going to go, that's not a problem. 1/2 N2, that's gone, not a problem. It's the H2 that's a little confusing. If fractions are bothering you, then think of it more like a decimal, okay? On the left-hand side, we have 0.5 moles of hydrogen. On the right-hand side, we had 2 3/2, that's 1.5. So 2 plus 1.5, that's 3.5. 3.5 on the right-hand side, 1/2 on the left-hand side. You can get rid of that 1/2, which leaves you with just 3. Okay. So that was a little bit of a tricky situation. Okay, now, let me give you one other piece of advice on these Hess's Law problems. Okay, I'm going to go back to the original problem here. As I said to you guys, my suggestion is to look at the equation you're supposed to end up with and take it piece by piece. Let me call your attention to a situation that will come up, guaranteed. So, listen here. Okay? When you're going through piece by piece and you're saying, okay, CH4, where is it? Okay, here it is. It's only in one place. Fine. There are going to be occasions where you come across some part of your final reaction that is not just in one of your elementary steps, it's in multiple. And how do you know how to deal with that situation? My suggestion is, okay, let's say, for example, I don't know why you would do this, but let's say in your thought process, instead of working from left to right, you decided to start with H2. And you said, okay, H2, where is it? Here it is. Oh, but wait, it's here and here as well. Which elementary step do I manipulate to deal with this? It's in 3 different places. If you come across something that is in multiple elementary steps, my suggestion, skip it. Don't deal with this yet. Go to a piece that only appears in one place. Deal with those first. What you'll find is, once you've dealt with this, this, and this guy works itself out naturally. Okay? So that is going to come up. Just be aware of that situation. Okay? And if you like these Hess's Law problems, at the end of my lesson today, I have a little challenge for you that I'll be offering a little extra something. Okay? Okay, ladies and gentlemen, I had you get a book for a reason. All right? And I can't believe I'm going to tell you to go to this page number, but in your textbook, please go to page 1059. 1059. All right, ladies and gentlemen. This chart that I have had you turn to, this Appendix C that is in the back of your textbook, this chart is your new best friend. Say hello. Hello. Okay. There is a lot of information in this chart that we're going to use frequently, both in this chapter and in the next chapter, chapter 19. And if you're just glancing at it, it's a lot. Now, let's use some common sense here, because this question always comes up. Do you think I'm going to have you memorize anything out of this chart? No. Have a little faith in your instructor, okay? No, I am not going to have you memorize anything out of this chart. Okay, but let's look at what's in here. Okay, you'll notice that we've got elements and compounds. They are listed in alphabetical order by name, not element symbol. Okay, so for example, potassium is in with the P's, not the K's. And you've got 3 columns for each element or compound. You've got delta H, delta G, and S. What's delta H? We know what that is. Change in heat, enthalpy. Delta G, we haven't talked about yet. S, we haven't talked about yet. We'll get to those in chapter 19. Okay? But the first thing that I want you to notice, do you see in the heading for the delta H column, do you see, it's really, really small, a teeny tiny little degree symbol. Do you see it? Okay. I need you to know what that means. That little degree symbol does not mean degrees Celsius or Fahrenheit. It means the numbers in this chart were measured under what's called standard state conditions. Okay? Standard state conditions, not to be confused with STP. Now, why the people in charge of these things chose to come up with 2 separate sets of conditions and give them almost the same exact name, why they would do that, I don't know. I think that's just mean. But let's just review, okay? STP stands for standard temperature and pressure. What is standard temperature? 0 degrees Celsius. What's standard pressure? 1 atmosphere. Okay, we're going to see some overlap. Standard state condition, okay, includes the same pressure. Okay. Now, guys, I want you to just scan your eyes down this chart. Do you notice that you are given states of matter for everything in this chart? Solid, liquid, gas, aqueous. Anything in this chart that is a gas, and you're pulling a number out of this chart, you may assume it was measured under a pressure of 1 atmosphere. What is this in other units? Torr?
760.
760, very good. Okay. Here's something that is not in the conditions of STP. This is unique to standard state conditions. Anything that is a solution, which means anything in this chart that is what state of matter? Aqueous. Anything that is aqueous, the numbers out of this chart were measured when these solutions were at a molarity of 1. Okay, you may assume that. Here's something else that's different. Standard state temperature is not 0 degrees. It's 25. Now guys, that's not just a random number. Do you know what that is? Room temperature. Yeah, 25 degrees is considered room temperature. Okay, now because we live in the Arctic here, we are not at 25 degrees. We are in fact at 18.5. But, no big deal. But that's considered room temperature. Okay, now, the other thing I want you to notice in this chart, look at the heading again for that delta H column. Do you see that there is a subscript F? Do you see it in the chart? Okay, F stands for fun. No, just kidding, no. It stands for formation. Okay? Now, let's think, like, let's take our brains out of here. Let's put our brains into your English class. Can you give me a synonym for the verb to form? Give me another word. To form something. To create, to make, to mold. Okay? I'm going to use a chemistry word. To synthesize.
Ooh.
Fancy. Okay. Guys, formation means synthesizing, and it means something even more specific than that. These heat values that are in this chart are some very specific heat values. It's the heat associated when a compound is formed from its elements. And not just any amount of compound, it's a very specific amount. It's the amount of heat associated when 1 mole of a compound is created from its elements, okay, under standard state conditions. So, let's get to know our new best friend here, okay? Find in the chart, remember they're alphabetical by name, find for me the heat of formation value for calcium sulfate. Find it. What's the number? Okay. Calcium sulfate's heat of formation. Ladies and gentlemen, let me help you understand what that number means. When this compound is formed from its individual elements, that means if I bring a piece of calcium metal, solid sulfur, and some oxygen gas, those 3 elements together, and I smush them together, there will be a large release of heat. This is negative. When I bring these 3 elements together to create calcium sulfate, there will be a large release of heat. Would that feel hot or cold to my hands? Hot, very hot. Okay. Okay. Let's continue with this chart. Find for me solid iron. Solid iron. Find it. Tell me the value. 0. Okay, what? Maybe it's a fluke. All right. How about solid scandium? Solid scandium.
0.
0. Okay. Let me ask you a question. How do you create an element? You don't. You don't create. You don't. Listen. You don't form elements in nature. You go and you find them in nature. So, and I know what some of you are thinking. Hold on, I will get to that thought. I can see it like scrolling across your foreheads right now. But, okay? Pure elements in their natural state, the way they are found in nature, you will notice, have values of 0. Okay? Here's what some of you are thinking. Wait a second. Wait, she's making this up. She's just making this up. There are definitely elements in here that do not have values of 0. Miss Giordano, okay, maybe you should read a little more. I got it, okay? Remember what I just said, though. Elements in their natural state. For example, find pure potassium in your chart. Pure potassium. What's the value in its solid form? 0. That's how potassium exists in nature. Look at the thing right above it. Potassium gas does not have a value of 0. Ladies and gentlemen, I want you to think about that for just a minute. Potassium is a metal. Metallic gas. That probably doesn't feel too good going in your lungs. Okay? But the point is, it has a value because to have potassium gas, you'll notice the value is positive. You have to put energy in to get that to exist. Okay? So, here's the deal, guys. As I told you, am I going to have you memorize anything out of here? Absolutely not. Now, on our next test day, am I going to, if you need a value out of this chart, am I going to let you just get up and go over to our cabinet here and grab a book and start looking things up? No, I'm not going to let you do that. That's crazy. I have to give you the information, okay? Like I will, on the test itself, give you like a little mini chart that has the information in it. Do I have to give you values of pure elements? No, I don't. Because I'm assuming you know that they're equal to 0. Okay? Maybe I shouldn't assume, but I'm going to. Okay, now. Something that may come up in multiple choice is, what is an equation of formation? Okay? Where do these values come from? And I gave you the example of calcium sulfate, but let's look at another one, okay? This is a compound called methanol. Equations of formations, as I said, guys, have some very specific requirements. Requirement number 1, how much of these compounds are we forming? 1 mole. Please notice, ladies and gentlemen, my product, this compound I am creating, has a coefficient of 1. It has to. An equation of formation, that must be a coefficient of a 1. That's requirement. That's the first requirement. The second requirement, what is on the reactant side? The elements in their pure natural state. These are N2 and O2 because these are diatomic elements. Why is there a fraction there? Because this has to be a 1. I don't get a choice about that. In order for this to be balanced, I can only use a fraction there. So let's write this out. This is so simple. Okay? This is my product. There are 3 elements that create it. How do you write carbon, pure carbon by itself? How do you write that? C. Plus, what's the next element? Hydrogen. How do you write hydrogen by itself?
H2.
H2. How do you write oxygen by itself?
O2.
Very good. And then methanol is my product. Must have a coefficient of 1. How do I back solve this? How do I fix it? To balance it. All right, 2 in front of the hydrogen. Very good. Congratulations, you just wrote your first formation equation. Don't you feel proud? I know. It's a big moment. It's a big moment. Okay. So let me show you what we're going to use this chart for. If you guys would, I should have had you take this out at the beginning of class. Take out your equation sheets, please. All right, on the back of your equation sheet, ladies and gentlemen, there's a section that says thermochemistry. Move your eyes to that section. And I'm going to show you what this chart will be used for. And guys, I'm going to put an equation up on the screen that when I first put it up, everyone kind of freaks out a little bit because it looks like it's written in hieroglyphics. Okay? Yeah. Yikes. Okay? It looks like something that is super complex, but I'm telling you, it could not be simpler. A second grader could do what I'm going to show you we'll do with this. Okay? This is on your equation sheet. You don't need to memorize it. It's there. But let's kind of simplify this. Again, I'm telling you, this is something that is so simple. What do you think these little letters mean, RXN? Reaction. The heat change for the overall reaction. That's what this is. Okay, this is the Greek letter sigma. What does that mean mathematically? The sum of. Okay. The sum of. This little n means moles, but let's keep it simpler. Coefficients. That's what this is referring to. Is what is your coefficient? And these, ladies and gentlemen, these are the values out of the chart. These are heats of formation. The values out of the chart for all of your products added together minus the heats out of the chart for all of your reactants. That's it. Let me show you how easy this is. We'll do this one together. Okay? So it says using this appendix, okay, this chart, we're going to calculate delta H for this entire reaction. Here's what I do. Okay, I'm going to put a big set of brackets. Products minus reactants. Products first. Go in the chart. I think it's with the carbon compounds. Please find CO2 gas. Make sure you're looking at the correct state of matter. And tell me that value once you find it.
Negative 393.5.
Okay, he's got it. Negative 393.5. Now, it has a coefficient of a 2 in front of it, so here's what I'm going to write. 2 times negative 393.5. Now, that's not my only product. Be careful with your state of matter. I believe this is with the oxygen compounds. Find H2O in its gaseous state. Find it in the chart. Negative 241.82. This one has a coefficient of a 3 in front. And then I'm going to close the brackets because that's everything for my products. Products minus find this guy. This is a compound called ethanol, although it's going to be in with your carbon compounds. Find it. Liquid form. There we go. Someone just said it. Negative 277.7. It has a coefficient of a 1. And last one. Thank you. You shouldn't have even been looking down. It's a pure element. 0. All right. Okay. You put all that in your calculator. This is what you get. Or something pretty close to it. And what would my units be? Okay. She says kilojoules per mole. Probably because that's the unit given in the chart. Okay. All of these values. Kilojoules per mole, kilojoules per mole. Well, guys, she's close. That is kilojoules per mole, but when you multiply, go ahead.
We multiply it all by the coefficients, which are a number in moles, so we're left with just kilojoules.
Right. When you multiply times a coefficient, you're really multiplying times a number of moles. Moles cancel out, so your final answer is just kilojoules. You guys do the second one. Be careful with your states of matter. Okay, so do you all agree this is super easy?
Yes.
I mean, this is literally just plugging numbers in and typing things into your calculator. Something that I get asked about a lot, ladies and gentlemen, is what's the difference between these things? Okay, you get this, this, this. Okay. First of all, if you ever see a delta H with no subscript next to it, you may assume that that is this one. Okay. These two things mean the same thing. The heat of the overall reaction. And that's your answer here, okay? This one, anytime you see that little subscript F or you see the word formation, I want like a little buzzer going off in your brain, and I want you to be thinking chart, 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 chart. You see the little F, I want you to think chart, okay? So keep those things kind of separated in your brain. All right, let's look at one more situation. This is what I'm going to show you on the next slide is about as complicated as I can make this, which isn't that complicated. Okay? It says, considering the following, it's already balanced for you. Now let's see if you were listening about 30 seconds ago. What is this? It has no subscript. It's for the whole reaction. This time, I'm not asking you to calculate it for the whole reaction. This time, I'm giving it to you. So what am I asking you to find? This. Now, where does your brain go? Chart, chart, chart. Okay, look in the chart. Chlorine. Find it. Ha! It's not there. I got you. Okay. I know. I'm just a mean person. Okay. Now, honestly, it says calculate. Now, would I really put a problem up here where all you had to do was go and look something up? No. I know. I shouldn't have tricked you that way. Okay. It's not in the chart. But so there must be a way to get it. You have the total final answer. I imagine some of these other things in the reaction you will be able to find. Figure it out. If you did not get the right answer, it is likely an algebra issue. Okay, you got to be real careful about distributing that minus. Let me ask you another question here. Why is there a 2 there? Yeah, there's a coefficient of a 2. You just need to be careful. I saw a couple of people ignoring that. That plays a role. Would you all like a challenge, Hess's Law?
Yes.
Why not?